Let's continue on with this. So this graph, it basically means that once the current, once it goes across the inductor, it takes a while for the induced voltage to go from 0 to max. So as we were saying before, that the voltage will be 0 once there is a current in the inductor, but it actually it precedes the voltage by a quarter of a cycle. Actually, no, it lags behind the voltage by a quarter of a cycle, as we can see here in the graph. When the voltage is a maximum, then the current is 0. So like right here, when delta V is max, the current is going to be 0. So current is always going to be behind it. So it's just a lag. So that's our graph. And then we have the phasor diagram that shows the same thing in vector form. So we have this here. So this vector represents the maximum voltage, and this would be voltage across the inductor. And this is the magnitude. This is basically the magnitude of the voltage, the delta V max, the amplitude of the voltage, the maximum amplitude. Then to represent that the current lags behind the voltage by 90 degrees, we see that the current maximum is larger than delta V, and it fits 90 degrees behind the maximum voltage. So that's what we see in the phasor diagram. So the current itself goes to maximum voltage, or goes to maximum current rather. It goes to Imax in an inductive circuit when cosine omega t is plus minus 1. And cosine omega t is only 1 at 0, and it goes to positive 1 at 0 and negative 1 at 180. So at maximum amplitude, let's say here, that would be 0. And then down here would be 180. So that's why you see the current maximum only at those points. And then for the sine function, it's maximum only at, pi over 2 and 3 pi over 2. So it's going to be ahead of the current by 90 degrees. So maximum current only at plus minus 1. So we can see that here. Delta V max over omega L. And so when cosine omega t, when Imax is equal to its maximum, cosine omega t is equal to 1. So that's why this is understood as multiplied by 1. So this equation just becomes Imax equals delta V max over omega L cosine omega t equals 1, which is, or cosine of 0 equals 1. And so that just becomes delta V max over omega L. And this is a magnitude because this current is a maximum at plus minus 1. So this is just the magnitude of the current. Okay, let me pause right here. Okay, so this is similar to Ohm's law. Ohm's law just is a relationship of voltage to resistance, or voltage to current, where we have resistance is delta V over I. And if we solve for the current, it'll be delta V over R. So we have this similar situation. So omega L acts like a kind of resistance in the inductor. It's not actual resistance because this current's still going to flow. A resistor's job is to impede or stop the flow of current, but an inductor will still have current flow through it. It won't act like a resistor acts, but there is some kind of reactance to the flow of current. And so therefore we call this term omega L the reactance of the inductor. Write that out. Similar, like a resistance. Since it is an inductor. This resistance depends on omega. So depending on the frequency, there's going to be different reactances. Reacts differently. basically the frequency of the circuit. And we'll talk about resonance here in a minute. So a particular AC circuit, where the frequency of the voltage source is the same as the frequency of the current, the circuit is said to be in resonance. And we're going to get to that. But the term omega L is called an inductive reactance. And we'll denote that by the symbol capital X is omega L. So we have maximum current through the inductor equal to maximum voltage divided by X sub L. So this would be the highest amount of current in the positive or negative direction as it oscillates, sloshes back and forth, because remember that the entire circuit is powered by an alternating current voltage source. So the current changes direction, positive, negative, as it goes through the entire circuit. And so the RMS values, similar. So remember, basically the root mean square values is the value of the current that's above the zero axis, above the horizontal axis. Because if we look at the maximum current throughout the entire circuit, the time average is going to be equal to zero, because there's going to be the same amount of time for the circuit to appear in the positive domain as it is in the negative domain, so it cancels out. So we look at the RMS, the root mean square current, which is basically the square of half of the maximum voltage squared. So it's basically this 1/2 I squared max, and then since we want I max and not I squared, we will then take the square root both sides, and that comes out to be I max over rad 2, and that's basically your RMS. The square root of the square root of half of the maximum current is your RMS current value. And so that's the important current in an alternating current circuit. Not the maximum current, we look at the RMS current. So that equation becomes IRMS delta V RMS over XL. Because we're concerned with RMS, not the max. This can be termed as the average value. The average of the average. We'll see. Basically, it's halfway. It's half of the IMAX current. So you could say like an average value. Let's see. For a given inductor, before a given voltage. Across an inductor, The frequency is going to increase, and then the current's going to increase over time. Over time, the current increases. And so the alternating voltage source is going to increase the frequency of the current. Then the frequency increases, or the current increases. The frequency of the circuit increases, then the current increases. That increased current creates, obviously, its own magnetic field. Then there is an opposing magnetic field that sets up its own current to oppose the original current. So we have this cyclic action happening. So there's a magnetic field around this guy. Then as this magnetic field increases, there is an induced magnetic field that creates its own current to oppose this current. And that causes the original current to decrease. So this is a constant back and forth within the inductor, even as the circuit operates under an alternating voltage or an alternating current. An alternating voltage source that produces an alternating current. And then within the inductor, we have this action happening. So this is back EMF that's produced from a new magnetic field that creates this back EMF to oppose the original current. And so now the original current gets smaller because now it has a resistance from this new current. There's a lot of action happening within the inductor and the circuit. So next thing. From the previous equation, therefore, delta VL equals negative delta V max sine omega t. And we know that V max, we can get the maximum voltage from this guy here, and it's going to be I max times the reactance of the inductor. Okay. And so that would be the voltage across the inductor in an AC circuit. Okay, so next section is how do capacitors behave in an AC circuit? So let's say we have a simple circuit, looks like this. We got a capacitor, and then we have an alternating voltage source, not just a regular battery, direct voltage source, capacitor. And so my voltage is going to be, again, a maximum amplitude, delta V max, sine omega t. Let me write that larger someplace else. It's a sine function, and the amplitude is V max. So again, applying Kirchhoff's rule. So we just have one alternating voltage source, and we have one loop, no junctions. We're just going to look at the how the voltage drops occur in this circuit. Again, we're going to use the loop rule. We're going to take the voltage source, the alternating voltage source, plus the voltage drop across the capacitor. The sum of those voltages are going to be equal to 0. So that comes out to be delta V minus Q over C, because from capacitor first principles, we know that delta VC is Q over C, and that's equal to 0. And then, so therefore, we set these guys equal to each other. That's going to be Q over C, and that's going to be delta VC, which is the same thing as the voltage source. Same, right? That is the voltage drop across the capacitor, as well. It's the same as the voltage source. Shouldn't be too serious. Okay. Solving for Q, we get Q is equal to C delta V max sine omega t. So far, so good. You guys are tracking what kind of function this is, right? You know what that looks like, right?
Yeah.
Okay. Plus, minus, V max, and on throughout the circuit through time. So this equation here just talks about the instantaneous charge on a capacitor. So basically at some time t, we have a charge Q. And that's nice, but we're interested in the current, as we have been for all of these other circuits, the current and the voltage, because we want to get the dependency or the relationship of current and voltage in an AC circuit for all these different circuit elements. And then after that, we can draw the phasor diagram and see how it looks, I look at it from a different point of view and, talk about what's going on. Now, we're interested in a current, not charge. We dealt with charges already in RC circuits, like in chapter 28. For now, so we got to differentiate charge with respect to time, dq dt. And we do that by the result of that will be operation of chain rule. I'll just give this to you. Take 1 omega out of the sine function, and then that'll be C delta V. The derivative of sine omega t will just be positive cosine omega t. And so this is how the current through the circuit would look like. Now, capacitors don't conduct current or electricity, they discharge. And so this would be the current after the capacitor discharges, through the rest of the circuit.
Wait, Mr. Kelly, you took the derivative of that sine function, right?
Right.
Okay.
Sine omega t. So we take omega out, and then we're basically taking the derivative with respect to t, and that just becomes just omega. And then we take a derivative of the sine function, sine omega t, and becomes cosine omega t. D dt sine omega t, cosine omega t.
Okay.
All right. So, and using this trig identity, cosine omega t is equal to sine omega t plus pi over 2. What does that tell you? What do you think that means? Simplest terms as you can break it down. It means that the sine and cosines are all out of phase by pi over 2. So the cosine function leads the sign by pi over 2, positive. So we have at t equals 0, this is a maximum, this is 0. So this is already leading, cosine leads sine by pi over 2. So using this trig identity, we have, if you will, current across the capacitor, but it's the discharge of current of discharging charge as a function of time, so dq dt, omega c delta v max. So basically put this down here, sine, if I could squeeze that in here, sine omega t plus pi over 2. So this time, the current and the voltage are out of phase by positive 90 degrees. So the we're going to see that the graph of the current is not negative pi over 2 as before with the inductor, that it lags the voltage. This time, the current across the capacitor leads the voltage. Okay, by pi over 2. So that's what the math will tell us. And physically, that basically means that as we're building up charge, there is going to be a current occurring after the capacitor discharges that precedes the voltage, or that as this current is building up, this current is building up before there is a potential difference, a maximum potential difference across the capacitor. So the current comes before the voltage in this case. Current and voltage. (90 degrees), 2 radians out of phase. So remember that voltage across the capacitor is delta V max sine omega t, and the current across the capacitor, a bit misleading nomenclature, but the discharge is going to be omega c delta V sine omega t plus pi over 2. So this one, current leads the voltage. We can just see it in the math. And then we graph it. And so we have something that looks similar to this. And then the current is going to be 0 when voltage is max. And then this is going to be max when this is minimum. Come over here to 0. Try to get this as fitted as best as possible. And backwards, I usually just make this into, overlap this with red. So the main idea to think about with the capacitor is that current comes before the voltage across it. it's going to lead it. There's a buildup of charge in the capacitor. Then we have our phasor diagram that depicts the same thing. Let me erase this. So if I have my delta V max as usual, and this is going to be the maximum voltage in the capacitor. And then here will be my current after the capacitor discharges. And so that's going to lead, because remember, this is a whole unit circle action. It's going to lead it by 90 degrees. And here's omega t as it wraps through 2 pi radians. Leads voltage by pi over 2. So this is a regular sine graph, sine and cosines, sinusoidal. And delta VC and IC, IC. And this is my phasors. It's basically depicting the phase shift between the two. You can think of a phasor diagram as a phase shift diagram. Because in cosine omega t plus phi, we're looking at the sinusoidal nature of this AC circuit. And we're looking at the phase shift relationship between voltage and current. Hence the 2 graphs. And more evaluation. The capacitor builds charge, and there's going to be a discharge. So for the sake of argument, we're just going to say it builds up charge and current, but it doesn't conduct like a wire or the rest of the circuit. There's a discharge. For current to flow through the rest of the circuit, and we'll just summarize all that and say capacitor builds charge and current, a quarter of a cycle before voltage. Why a quarter of a cycle? Because 90 degrees is 1/4 of 360. So again, the current reaches a maximum value when for all values of theta that make the cosine function equal to 1. And that occurs at 0 and 180, plus minus. Again, we're just evaluating what we see. And that's when theta or omega t is equal to 0 or 180. Plus, minus, positive, negative. Now it's flowing through time. Okay, so there's this is a wave. Think there's like a wave of electricity through your circuit. And that's why all this stuff really just comes down to waves and frequencies and energy. Because our circuit, we can make our circuit behave like a mass on a spring, which is essentially what's going on. We just now change our parameters, we change our context. We have an electric field instead of a gravitational field. We have an inductor instead of a mass. And 1/c instead of spring constant. Instead of a resistance constant, we have an actual resistor. Alternating voltage source to get these different dependencies. Current to voltage in the capacitor case. In the inductor case, it's down here for the current. And then for the resistor case, it's in phase, because that's just like a normal, ordinary circuit. The resistor has no kind of buildup. It's going to be direct. So we have a one-to-one relationship. That's how we get Ohm's law. So we're starting to put it all together. Now let's talk about all those reactances and and then we're going to combine everything. We're going to have an RLC circuit, and we're going to see how everything fits, behaves when it's all at once. That's like kind of a real circuit. Most general. Okay, Imax omega C delta V max is equal to delta V max divided by 1 over omega C. And that's just solving for V max. Solving for Imax. So we just divide by the reciprocal in order to get the same form. So we say term 1 over omega C is called the capacitive reactance. How does the capacitor react to this discharge governed by the 1 over omega C, very similar to omega L. And therefore, we define the capacitive reactance 1 over omega C. And that's basically, yeah, well, it's the same thing. This becomes, oops, hold up. That becomes this and vice versa. Okay. Whoops. Therefore, the maximum current is delta V max over X of V. Now, we can re-express delta VC. So we got everything for Imax for the capacitor. Now we're just basically mixing and matching for Imax and VC once we know the capacitor reactance. Now we can substitute that into the original equation. One second. So that's delta V max sine omega t. That was the original equation, and we have that equals to I max xc sine omega t. So you have a problem. I want you to find the voltage in an AC circuit with a capacitor. The parameters you can use for that. So again, we can take a look at this capacitor reactance equation here and talk about that. As the angular frequency, I'll just say frequency of AC voltage source gets higher, okay. as that increases, the capacitive reactance decreases. If you have a AC circuit with just a capacitor, drive up the frequency, let it cycle faster, and then the reactance in the circuit is going to go down, and then we're going to get maximum current. So this is something for an engineer, a physicist, anybody. Knowing that this is your capacitor reactance, you can play around with the variables in order to get increasing current, decreasing current. As omega goes to 0, the current goes to 0. Basically, we're turning off the voltage source. And then, basically not useful. So again, if you now reduce the alternating voltage source to basically no frequency, it's not cycling. It basically becomes like a battery, a regular battery, a regular direct current circuit. Just evaluating everything. This is the RLC circuit. We're going to combine everything here. Here we have a resistor, inductor, and a capacitor in series. An AC source. Now, AC source has an applied voltage, of course. That varies through time. Just, keep reminding you of how this alternating voltage source is going to work. It's going to work sinusoidally. The current is going to be I max. Sine omega t minus phi. That means that it's going to be cosine, so that the current is going to lag the voltage. So
Wait, Mr. Kelly,
yeah,
the phi was, what was phi?
current. So current in the AC circuit. It's just
Oh,
to distinguish it from this I max, but it's the current.
okay.
So we've already seen the cases of Imax and voltage being in phase for the resistor circuit. And in the inductor circuit, the voltage is going to lead the current by pi over 2. And then in the capacitor circuit, which you just saw, the voltage lags behind current by pi over 2. So now we're going to represent all that in a phasor diagram. And that's in turn going to allow us to talk about the voltage in an RLC circuit, current, and we're not going to talk about individual reactances, the inductive reactance, the capacitive reactance. We'll talk about overall RLC reactance that we call impedance. It's going to be the sum total of all the reactance in the circuit, the resistor resistance, the reactance of the resistor resistance. capacitive and inductive reactance all together are going to form what is called the impedance. RLC. So okay, so this equation here is basically saying that the current is going to lag the voltage. Like when the voltage is a maximum, the current is going to be at zero. This is just one moment in time that the current is lagging. So far we've seen that usually I, or just say the little I to distinguish from I max, and delta V will be out of phase. So since the RLCs are in circuit, this is the RLC circuit. Since the RL and C are in series, there's going to be the same amplitude and phase for the current, because that goes back to series circuits, that we're going to have the same current through all of these circuit elements. And our job is to get what that current is going to be in that circuit, and also the voltage and impedance that we call, well, impedance, which is going to be a combination of all the reactances. And so forth. So the current is going to be AC. It's not going to be direct because we have a AC voltage source there. And so since these guys are in series, there's going to be the same amplitude and phase for current in an RLC circuit. So our job is now to determine what the phase shifts are, for all those elements, as well as the maximum current. What is the maximum current in this RLC? Okay. On the resistor circuit, the alternating current and voltage are in phase. For the inductor circuit, we found that delta V leads by pi over 2. It leads the I, current I, by pi over 2. In the capacitor circuit, delta V lags I by pi over 2. And that looks like, again, the voltage in a resistor circuit, maximum amplitude current times R sine omega t, which is delta VR sine omega t. Voltage in an inductor circuit, I max XL sine omega t plus pi over 2, because we know that the voltage is going to lead by pi over 2 plus delta VL cosine omega t, and the voltage in the capacitive circuit and it's going to lag the current by pi over 2. So it's negative VC cosine omega t. So these are things we've seen. With all voltages have different phase angular relationships. In a phasor diagram, we can't just add them up together, because remember, those are vectors. Must add them vectorially. And let me make a correction there. They're not all vectors. It's just that they have different phases, so we can't just add them together. They're out of phase, they're different phase shifts. So in order to get what the phase shift for this entire circuit, we have to add all of the phases vectorially. So as follows, so we have combo, phasor diagram, where for the resistor circuit, the current and the voltage are in phase. The voltage and current in an inductor circuit, well, the voltage leads this current by 90. So this is just a sample way of doing this. And then in a capacitive circuit, the voltage lags behind the current by 90 degrees. So current is in common with all of these different voltages in phase with the resistor. Voltage leads by 90. And then here we have a lag by 90. Okay. So in this picture, as we can see, is a unit circle. The Imax is going to be equal to 0 for this picture. And so, this is our reference level. So we see that delta Vy, or all of the voltages on the y-axis, is going to be delta VL minus delta VC. We can see that here. Oops. The delta Vx is equal to delta Vr. That's the only voltage on the x-axis. And now for the maximum voltage in this RLC circuit, which is just going to be the vector sum of all of these voltages, because as we've seen in individual phasor diagrams, that we get these vector arrows represent the magnitudes of the maximum voltage. And so for the RLC, we have to vectorially add together to get the maximum voltage for the RLC circuit. And then that looks like this. Pythagorean theorem, delta V squared, Vy squared. Delta Vr squared plus delta VL minus delta VC squared. And so we know that the voltage in a resistor circuit, alternating circuit with a resistor, is going to be I max R squared plus I max XL minus I max XC squared. Squeeze that in there. So delta V max is going to be to factor out this I max, square root of R squared plus XL minus XC squared. Therefore, the maximum current, because we're always looking at the relationship of current and voltage, I max is delta V max over R squared plus, and that is the maximum current in an RLC circuit. Okay, I'll just leave it like that. Do I have space or no? Nope. Okay, 1 second. So now we have a term for the maximum voltage RLC. The denominator, the total RLC resistance, we call the impedance. So the overall resistance in an RLC circuit is called the impedance Z. It's getting kind of funny here. Okay, the impedance Z given by R squared plus XL minus XC squared. And we can just generalize the I max by saying delta V max over Z, because we had omega L for the inductor, 1 over omega C for the capacitor, and now Z just for the R, L, and C. So this is the AC equivalent of V over R, the Ohm's law. So the impedance is proportional to RL, C, and omega, all the different reactance frequencies. It's just a function of all these guys. Now, in terms of the phasor for the maximum voltage, we can take a look at the, combine all the phasors together. So we have I max, which is equal to 0 for the resistor circuit, just in this orientation. And then we have delta VR. So be delta VR. And so we have already seen that in the Y direction, that the total of the voltages in the Y direction are going to be VL minus VC. And since VL is greater than VC, it's going to be a positive. And so therefore the phasor for the maximum voltage in an RLC circuit is given as this figure, this right triangle. This is vector result that we see here, which is a vector sum of VR, delta VL minus delta VC, and then there's going to be our phase angle there. So we've now graphically found the phase angle the maximum current and the maximum voltage for an RLC circuit, at least vectorially there. We can figure out what the phase angle is going to be by using inverse tangent, because tangent of phi, opposite over adjacent, and we'll get phi is going to be equal to, so I'll have to do the middleman here, delta VL minus delta VC over delta VR. Becomes inverse tangent I max XL, I max XC, I max times R. And then we can further simplify that to be XL minus XC, because these I's can cancel out. So if we know all those values, we get the phase angle for the RLC circuit. Some evaluations, if XL is greater than XC at high omega, phi is greater than 0, then this circuit, this RLC circuit, would be more inductive than capacitive, because there's more of an inductive reactance than a capacitive reactance. So the inductor would dominate in this circuit. And if XL is greater or less than XC greater than XL, if XL is less than XC, the phase angle is less than 0. We'll get this evaluation from this equation up top. And so more capacitive and inductive. And if they're equal, the entire circuit is purely resistive. So the resistor would dominate. So it all depends on the frequency values. That would, in turn, well, the frequency is going to be the same for everything. It depends on the value of the inductor, the capacitor, the frequency given. And in that case, if we can tailor all those such that the reactances of XL and XC are equal, it's a purely resistive circuit. The resistor dominates. Now that's a lot there. It's a combination. The RLC is always going to be the most general, longest case to consider in any type of circuit, whether it's alternating or regular direct current circuit, as we saw in the previous chapter. But
and the phi is equal to 0 over there, but for the purely resistive one.
yeah, it would be, because we wouldn't have a phase angle. Yep. Exactly. Let's take a look at power in an AC circuit. That may be it for today. I don't know. Let's see how fast we go. I have everything done for what I want to cover in 34. I'm not going to cover all of 34. I definitely want to wrap it up by tomorrow. So 33.6. So power in an AC circuit. So we know power is I delta V, I squared times R, and V squared over R. And we're going to look at it in terms of its, the RMS values. Let's develop that. From delta V equals delta V max sine omega t. These are just the general relationships that we've developed since the beginning. From those, we can find the power in AC circuit. P equals I delta V, to denote it from I max and V max. And that would be, let's see, squeeze that over here. I max sine omega t minus phi, delta V max sine omega t. And then I max delta V max sine omega t sine omega t minus phi. So how can we represent this in a practical way? Well, we can make use of some trig identities, right? So knowing that sine omega t minus phi is equal to sine omega t. You can look up your trig table for this guy right here. Known identity, cosine omega t sine phi. The power, or maximum power, I max delta V max sine squared omega t cosine phi, because we're just manipulating this here. There was a sine already outside here, so we sine squared first and then cosine phi. And then next will be max delta V max sine omega t cosine omega t sine phi. Again, there was a understood sine omega t out there, and we just multiplied by this part of the identity. Let me get that. Let's simplify that. So if we take the time average of power, so it's going to be I max up, I max down, same magnitudes, and take them over time, we'll see that I max, V max, and magnitude are going to be constants. Because it's the same value up and below the zero, sines and cosines. So if we look at this first term here, again, another kind of identity, if you will, or relationship of this sine squared omega t function over time. The time average of this function basically is something that you can see. You've probably seen in your math classes, but I will just let you know that the time average of the first term in this power series, the power equation involves sine squared omega t, which is equal to 1/2. The sine squared function, the average, the time average is 1/2. The second term goes to 0. Therefore, we have average power, because we're looking at the average over time, is 1/2 I max delta V max cosine phi. So that's what it would be in terms of the maximum values. Also in terms of RMS values. IRMS, delta V RMS, cosine phi. And remember that RMS is the half of the maximum current. It's basically square root of the square of this, which is equal to that. And so when we square root all of that, we get the RMS, which comes out to be 1/2 IMAX. Actually, it's going to be rad 2. Yeah, it's going to be radical 2. But we put RMS here simply because we're looking at the average over half of a cycle. And so we just basically substitute that as RMS because we're looking at average, not what RMS is, but the average of that. You know, so we don't get radical 2 here. We just get 1/2, which is going to be our IRMS over our time average. So we just make a substitution in terms of RMS, and that's what we have for power. So that is average power in terms of RMS. That. And so now we say that the cosine phi is known as a power factor. And then the voltage across the resistor, everything kind of still checks out because this cosine term just keeps coming along. So it's just a factor, power factor of the voltage in this, situation. It's power factor and delta V max. Across the resistor is delta VR equals delta V max cosine phi, which is also equal to Imax times R. And knowing that cosine phi equals to Imax times R or delta V max, because this is a unitless quantity. This is voltage over voltage. We can now go back to this equation, use this substitution to simplify the average power even more. So we have average power equals IRMS delta V RMS cosine phi. We have a expression for that. So IRMS delta V max over radical 2, because that's your, your RMS value is a voltage, cosine phi, I max times R. Delta V max. Let me go back to this part, because admittedly, I flubbed that explanation. So this is what it really is. It just, rethought it, just looked at the equation and I'm like, wait a minute. We know that power is I times delta V, that's one expression. So in terms of the RMS values, just put I RMS delta V RMS, that's it. Which you can look at power in terms of the max, current and voltage, or the IRMS. So this is much more efficient, I would say, in context with our AC current, AC circuits. We look at power this way because we're looking at we're mostly concerned with RMS values anyway. So now onto this part, we substitute, cross those out. We get IRMS, I max times R, over radical 2. And guess what? That becomes I squared RMS times R, because this is IRMS times another IRMS squared root R. There it looks to I squared R. We have seen that in DC circuits. So now, we go back to the power equation. So this will be average power, I squared RMS. Now, if we look at the average power in terms of the power factor, IRMS delta V RMS cosine of phi. Well, we can simplify this even further. We can eliminate cosine phi for values of phi that make cosine phi equal to 1. And the values of phi that make that equal to 1, phi must be equal to 0, because cosine of 0 is 1. And that would be a case in this circuit, this RLC circuit, when it's purely resistive. In that case, when it's purely resistive, the current and the voltage are in phase with each other. And the phase angle, like you said, Edward, is 0. There's no phase angle. Well, the phase angle is 0 because they're parallel. I and the voltage and the current will be parallel. So therefore, cosine phi goes to 1 when phi is equal to 0, like this. So therefore, average power becomes I RMS delta V RMS, which we're familiar with, I delta V. So in this case, there would be no power losses when we're looking at that, the average power in a RLC circuit, because the phase above and below is, they're basically the same. Not only that, in this case, we have no phase angle. So no power losses in a capacitor and an inductor, simply because the phase differences are going to be the same above and below the horizontal line, the horizontal axis, at least from the graphical perspective. So we, in an RLC AC circuit, there's really no power loss. So that's definitely more efficient than a DC circuit. We're always going to get an accumulative power loss, but an AC circuit, we get none, at least on average. It's going to be a fringe, but on average, we get no power loss. So let me just write that out. So we get no power losses in capacitors and inductors in an AC circuit. No phase angle to consider. That also corresponds to a purely resistive circuit. So this is perhaps the most efficient circuit. It is definitely way more efficient than direct current. And let's see. I think with that, that'll be a good stopping point. Yes, go ahead.
I have a question. We've been going with the average power so far. Can we also calculate the maximum power that is possible?
Well, since this is all cyclical, we have two plateaus. We have two parts of the circuit where it can be maximum. There is no real such thing as a maximum power, because we're averaging between both of the maxes above and below zero.
Okay.
We can look at maximum amplitude of current and voltage, but power is just like an average.
Yeah, okay, got it.
So we'll continue next time, tomorrow. The rest of 33, 33.7, we'll look at resonance. Try to just be very general with that. I mean, I definitely like to be at the details, but I want to save time for 34. Definitely take a look at transformers. Basically, transformers are devices that take power from your power station way out in the mountains, 400,000 volts or however many, 700,000 volts, hundreds of thousands of volts coming from there to different distributor stations. That's going to step that voltage down, in one leg of the trip, and then there's going to be another step down transformer in your, you could go to your streets and you can see all these little cylindrical boxes on the phone poles. Those are more step down transformers, and that leads to your house, and then there's another stepping down to 120 volts AC, and then you have within the circuitry of your home something called rectifiers, or I'm not sure how many rectifiers there would be. I'm not an electrical engineer, but we'll see what that rectifiers, what their main job is to take AC current and make it into direct current to be used by your appliances. So we'll take a look at that next time. Take a look at chapter 34, electromagnetic waves, and be done.